Hello everyone, so I am back and we are going to be talking about solids today and the different types between an ionic, molecular, and metallic solid, as well as solids are dissolved and how they dissolve and things like that. I do apologize in advance, this lecture is probably going to be a little bit on the long side. I'll try and go as quickly as I can, but I don't want to rush anything. Alright, so let's get started. And there we go. Okay. So there are a couple of different types of solids to understand. So we're not even getting into really the molecular versus ionic versus metallic yet. Let's just go into the two broad types. The first one is a crystalline solid. So it's going to have a very highly organized arrangement. The atoms are going to be alternating. It's going to look very orderly and organized like the first top two examples. Okay, a lot of our ionic solids are crystalline solids. The other type is called an amorphous solid. Now, these are disordered, okay? So they're not really, they don't fall into an orderly pattern at all. They're completely disordered, like glass or plastic. When you break a piece of glass, it doesn't break into nice little crystalline crystals and things like that. It just kind of shatters. So those are the two main types, and we're going to kind of talk about the properties that have to do with both those types kind of as we go through the lecture. Okay, so first off, let's talk about a crystalline solid. So it's going to be a very orderly three-dimensional system. And it's going to have this lattice. And this lattice is the actual orderly part. So you can see that you have, this is a LICL, that you have the Li and the CLs very organized. They have forces between them. So the Li is positive and the CLs are negative. So you're going to have a very strong attractive force. Remember, dipoles and hydrogen bonding are between partial positives and negatives. These are full partial and full negatives. So these are very strong. We would call these ionic bonds. Okay, but they make up a crystalline solid. So they're very orderly and things like that. Let's go into metallic solids first. Metallic solids, metals obviously are good conductors of heat, electricity, all kinds of things like that. And that's simply because they've got this kind of odd thing going on with their electrons. The electrons in a metal, remember they're all cations, right? So metals are always pluses, like Fe plus or Li plus or Cu plus, 2 plus, whatever have you. So they don't really want the electrons. They want to give them off. But you can't give an electron to someone else who doesn't want one, right? Everyone in the metal has too many electrons and they're trying to get rid of them. So what happens is they kind of all just give them up into this kind of free-moving cloud of electrons that really don't associate with one atom versus another, and they just kind of float freely amongst this solid, almost like a hippie commune, if you will, or they call it the sea of electrons, which is kind of a really cool visual, right? This sea of electrons where these metals are kind of sitting in this sea. They're stationed, they're stuck in place, and these, just electrons are floating around and by them, and that's what allows you to conduct electricity or heat, right? Electricity is an electron, so let's say I add a little bit of an electron to one side, it can float freely, or it can it's not bonded to an atom, so another electron could move off, and we would see that as an electrical current, right? Almost like a wave through the ocean. Electricity kind of moves through the sea of electrons. Okay, so it's kind of a fun little example. And this is one of the better pictures I could find with it. So you have these fixed metals stuck in place and these electrons just kind of moving around it. It's kind of cool. So yeah, it happens because they're all cations. None of them want the electrons. They kind of just give them off. They're called delocalized. Please note this only is true with the valence electrons. The core electrons are still orbiting the nucleus just because they have such a strong Coulombic attraction or strong nuclear attraction. It's the valence electrons that they're kind of just throwing out there and making it part of the group, if you will. Okay, now metals can form alloys, and alloys are kind of a weird thing, right? They're a solution, if you will. They're a solid solution, so it's a mixture. And all you really do is melt two metals and kind of mix them together, but some fun stuff happens. I guess an alloy doesn't really need to be two metals. So the first type of alloy is a substitutional alloy. So in this example, we have brass. Now brass is copper and zinc. And they use it because copper is too soft and it's pretty expensive. But brass, you want to be a little bit harder, but you want it to still be malleable and you don't want it to lose a lot of its properties of copper. So what they do is they mix copper and zinc, and just to see what you see on the right hand side of the screen. So we'll have mostly copper, we'll have mostly one. I can't really see, but they seem to both be pointing towards the gray circle. That's great, awesome. And then we'll just have, let's say, the zincs kind of just tossed in there a little bit. The zincs will substitute out the copper, or the copper will substitute out the zinc. They're roughly the same size, so the density doesn't change at all. And it's still very metallic-y. You haven't really changed a lot of its original properties. You might have made it a little bit harder, a little bit softer, a little bit more malleable, a little bit less malleable, but not a ton changed with a substitutional alloy. An interstitial alloy is very different. Okay, so an interstice, it doesn't feel like, an interstitial area is probably a better way to say it. That's like a space or little holes. And that's not true just for chemistry, that's a general term. You'll hear that in biology a lot as well, like the interstitial space between like the vertebrae in your back or something like that. But an interstitial area is just in between. So like in our example here, we have steel. So steel is made by mixing carbon with iron. So the carbon doesn't displace the iron, it kind of fits in between the big iron atoms. Remember, iron is much larger. Iron has a mass that's like 4 times larger than carbon. So carbon can kind of fit in between the irons. And so it's called an interstitial alloy. So we take these smaller nonmetals usually, and we pack them in between the metallic ions. Obviously, that's going to greatly increase the density, right? We're not changing the size of it, we're just cramming stuff in the spaces, in the free spaces. That's going to drastically increase the density, and it's going to change a lot of the properties. It's first off going to make it a lot more rigid, okay? Steel is much more rigid than iron. And it doesn't bend as easily, which is both a good thing and a bad thing, right? So if you don't want it to bend, that's great, but it also tends to be very rigid and snap or shear off, if you will. So those are the two main types of alloys. So a substitutional, we substitute out a metal ion for another metal ion, and they tend to be not change the properties too much. Interstitial, we toss in smaller atoms, they become much more dense and rigid and stronger. Okay. So, well, we need to talk about network atomic solids. These are covalently bonded things. The great example is like a diamond. A diamond is just carbon. Okay, so it's just carbon atoms bound to each other. So every carbon is bound to 4 other carbons, and those are bound to 4 other carbons, and those are bound to 4 other carbons. So you get this web of these covalently bonded carbons. And since it's this web, it's very strong, because there's no intermolecular forces, because they're all true bonds. So it's almost like an ionic, where everything is bonded to everything else, and it's just this very strong, rigid configuration. It doesn't bend very much, it doesn't deform, simply because everything's bound together. All right, diamonds are very, very strong, very, very high melting points. Another example of this would be a graphite. Okay, graphite is once again made of the exact same thing as carbon, or as diamonds. It's just pure carbon. The difference is that while carbon makes this 3-dimensional lattice, this bonded to 4 of everything else, this 3-dimensional lattice that's super strong, graphite bonds in sheets. So the other carbons that it bonds to will be in a flat plane. So graphite's actually sheets of carbon together. Okay, and what holds them together would be London dispersion forces. So we have covalently bonded along one plane, and it's held together in the other plane through just London dispersion forces. That's why it's very easy for you to write with graphite, because layers just kind of slough off or fall off. Whereas with diamonds, they don't do that. Okay, our last example is a molecular solid. These are a little bit different. These are like sulfur, S8, or phosphorus, P4. They're very strong because they have a lot of bonds within them, but they have very weak interactions between other molecules. We don't really deal a lot with molecular solids. It's important to note that they're there, but we don't do a lot. All right, so an ionic solid, and we touched on this kind of in the beginning. An ionic solid, they have these lattices, so every ion has this ionic bond to all the other ones. So we can't really, it's hard to say like, oh, NaCl is one Na and one Cl. It's more of NAs and Cls alternating, creating this three-dimensional space, like you see in the picture, right? Sure, we have one Na, we have one Cl, but really it's alternating. It's NaCl, 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 and it builds this three-dimensional thing. Now, they're held together by a strong electrostatic interaction, so think full charge difference, so think like dipole-dipole on steroids, like the Hulk of dipole-dipoles. So they're held together very, very strong, very low vapor pressure, right? NaCl doesn't evaporate when you put it out. It's got a vapor pressure of like 0. However, they do dissolve in water pretty well because the water can kind of get in between and separate and just kind of be, you know, that guy who breaks up other compounds. They do tend to be brittle because once they shift a little bit, you're going to get that charge differential is just going to repel them and they're going to break apart. So they don't deform like metals do. Metals deform because they're sharing electrons, and if one moves a little bit, no one cares. Well, they're held together so tightly that if they shift just a little bit, all of a sudden an Li that was next to a Cl, if it shifts, now we have two Li's next to each other and then two Cl's, and then they just break apart. It's almost like a chain reaction. Okay. So we need to talk about just their force generally and how to compare them. So the strength of that electrostatic force, that charge differential, that ionic bond, that Hulk of dipole-dipoles, if you will, is a function of two things, and it's probably not going to be surprising to you. Distance and charge, right? It's like everything else. It's a function of its distance and of how strong it is. We were talking about that with Coulombic attraction or nuclear attraction and shielding and all this other stuff. Distance and how strong it is. So, if we have something with a high charge, like Mg2+, it will be stronger than something with a smaller charge, like Na, 1+. Right? 2 pluses are stronger than 1 plus. Makes perfect sense. The distance is measured from the center of one nuclei to the center of the other. So if I have small atoms in there, that's going to be stronger. Right? Mg is stronger than Ba, just because Mg is smaller, and so these ions are going to be packed in tighter, and they're going to feel that attractive force stronger. The stronger the attractive force, the stronger its properties. Like, it'll have a higher melting point. It'll be harder. It'll have a lower vapor pressure. It will be more ionic in character. So certain things like, let's say BaCl2 is a salt. It's an ionic solid, but it's going to be softer and melt easier than a small thing like MgCl2. Right? And there's an equation that kind of goes through that, but you don't really need to know that equation. Just understand that a bigger charge differential makes it stronger, and so does a smaller atomic nuclei. Okay. So, like I said, we represent it in an empirical formula, the small simplified version, because we can't really do a discrete formula, right? That's, let's say, NaCl. How do we... It's just a ratio. It's a 1-to-1 ratio, and that's why we say it's like that. Okay, so we're on our last topic here. We're talking about dissolutions, or dissolving a substance. Now, ionic compounds, pretty much across the board, they dissolve in water, with few exceptions. And here's what happens. The water molecules come in, and they kind of wiggle in between the ionic ions. All right, so they kind of can get in between the ions, and when they do that, then it's kind of almost like a wedge, and they're able to separate them apart. All right, think of it like, let's say you're at prom with your prom date, and your needy friend comes in who's upset for whatever reason, right? She's able to get in between you and your prom date and separate you guys, and she's essentially dissolved you, right? She's dissolved you and your prom date because he's off, you know, drinking punch. I don't even know what you guys do at prom. Drink punch, have snacks. I don't know what goes on at prom. Anyway, so that's what water does. So water is able to kind of get in between the ions and separate them out. It's really important to realize that hydrogen in water is partially positive. So it's going to surround the negative one, right? Because positive and negative will attract. And then the oxygens, which are slightly negative, will surround the positive. So you can see that in the picture. The red ones are around the positive purple, and the white hydrogens are around the negative green. right? And this, happens. That's why increasing, let's say, the temperature of the water dissolves things faster, because the water molecules are moving faster, so they can get into those little crevices faster. Or stirring gets things dissolved faster. Or crushing, because the more you can expose that solid to water, to fresh water that's not already saturated with the dissolved stuff in it, the easier it's going to be to dissolve it. And this also ties in with saturation points, right? You can only dissolve so much salt in a liquid because at some point all the water is going to be surrounding ions, and there's not going to be any more water to wiggle in and break up those couples or those prom dates. So we kind of can talk a lot about dissolutions. We're going to talk a lot about dissolutions, but this is generally the idea. The water comes in, breaks them apart, and the oxygens go around the positive, hydrogens go around the negative. Okay. This also is the same thing for polar covalent compounds as well. It's not quite as easy to see. These are ethanol molecules, so they're an alcohol. They are asymmetrical, so they are polar. And the water does the same thing. The water can kind of get in between them and separate them out. Kind of wiggles their way in. Okay. And so then there's this rule of thumb, right? This is the last slide, I'm pretty sure. So the rule of thumb is that like dissolves like. This means that if I have a polar solute or ionic solute, it'll dissolve polar solvents will dissolve it. So for example, NaCl and water, an ionic solute, a polar solvent, water and salt dissolve. However, let's say I have NaCl and vegetable oil. Vegetable oil is nonpolar. Oil will not dissolve the salt. And that's because the oil molecules don't wiggle their way in between the compounds because they're not polar. They have no attractive force to do that, right? Water wants to get in there because it's kind of a little bit of polar. It wants to work its way in. Oil, it doesn't care. Why would it want to? It's nonpolar. On the flip side, though, oh no, it's going to restart my computer. Well, let's just postpone that. Don't want to do that. Okay. Nonpolar solutes will be dissolved by nonpolar solvents. Right? And we have some examples. I'm not going to read through them, but like dissolves like. Okay. So that should be it, and I hope all of you had a wonderful time. I certainly enjoyed myself. It was a blast. And I hope you all enjoyed it, and I will see you in class. Bye.